Lesson 10B starts with a fundamental counting principle. The first question says, a password must contain 5 unique lowercase letters. That means no duplications of letters. How many possible passwords are there? I want you to stop the video, take a minute, think about this, choose one of these 4 options, and then go through and explain why you chose the answer that you did. Without that explanation, you won't get full credit for your notes. Okay, so hopefully you have a good answer to that. Now let's look at the second option, or the second question. It says Jaden is choosing a cake for his birthday. He can choose one flavor of cake from 2 choices, a flavor of frosting from 4 choices, and we want to figure out how many different cakes he has to choose from. This one tells us to draw a diagram to solve the problem. So let's start by thinking about the cake. Okay, we have 2 choices for cake. It can either be chocolate or it can be vanilla. Depending on which cake he chose, he still has 4 choices of frosting. So now, off of each of those cakes, I'm going to have 4 branches for the frosting. We have chocolate, we have vanilla, we have caramel, and we have cream cheese. The same choices exist if he chooses vanilla cake. He still has chocolate, vanilla, caramel, and cream cheese. So for example, he could have a chocolate cake with cream cheese icing. That's what this line would represent. So each of these endpoints represents a unique cake. So we would have 1, 2, 3, 4, 5, 6, 7, 8 possible cakes that he could have. So if we think about this in terms of multiplication, looking at the fact that we have 2 choices of cake, and we have 4 choices of frosting, using a multiplication sentence, we would have 2 times 4 to get 8. And this is what leads us to our fundamental counting principle. The study of probability begins with this concept, and it is called the fundamental counting principle, which basically says if there are m choices for one thing and n choices for another thing, then there are m times n arrangements of the 2 combined. So let's see how this works out. An ice cream store sells 31 flavors. For how many days can you purchase a different 2-scoop cone every day? So in situation A, it says, let's say that the 2 scoops must be different, and strawberry vanilla is different from vanilla strawberry, because it matters which one you have on top. So I have the first scoop, and I have the second scoop to consider. So they have 31 flavors. So I have a choice of 31 possible flavors for my first scoop. Since I don't want to have the same scoop twice, I don't have 31 flavors. I only have 30 to choose for my second scoop. So then the fundamental counting principle says that I'm going to multiply these, and I'm going to get 930 different ice cream cones. So part B asks, how would this be different if we can have 2 scoops of the same flavor? If that's possible, then we would just have 31 choices for the first one, and for the second scoop we would still have 31 choices. And this is going to give us 961 ice cream cones. So let's look at here. This one wants us to draw a tree diagram. We have 2 types of cones, 2 types, vanilla and chocolate, or peppermint ice cream, so 3 types of ice cream, and chocolate or caramel syrup. So it's going to be very similar to the one that I did before, but I want you to stop the video and draw a tree diagram. Hopefully your tree diagram looks something like this. So if I wanted to follow this path, this would give me a waffle cone with chocolate icing and caramel sauce. If you count the ends, you'll find that there are 12 different options. We can also use the fundamental counting principle to get there, because for cone, I have 2 options. For the ice cream, I have 3 options. And for the syrup, I have 2 options. 2 times 3 times 2 is equal to 12. Okay, so let's talk about license plates. This is another very typical combination kind of problem. A license plate consists of 3 digits followed by 2 letters. So let's stop and think about what that means. Digits can be 0, 1, 2, all the way up to 9. These are your digits. So if you count those, this would be a total of 10 options. Letters, we're talking about the alphabet, so A, B, etc. up to Z, and there would be 26 of those. So in the first situation, we have no letter or digit can be repeated. So we have 3 digits followed by 2 letters and no repeats. So I would have 10 choices for the first digit, only 9 for the second, and 8 for the third. For the letters, I would start with 26, and then I would have only 25 choices for the second. And then we would multiply all of those numbers together, and we would get 468,000 different license plate options. Now, if they can be repeated, that changes this slightly. We still have 3 digits followed by 2 letters, but this time we have 10 in all 3 of the digit spots and 26 in both of the letter spots. So when you multiply this out, this gives you 17,576,000. So allowing the repeats gives you a lot more license plates. Okay, so now let's go back to the problem that we answered at the very beginning and see which answer is right. I want you to stop the video, do this one on your own. Your teacher will expect that to be done. All right, 7. Let's look at this one. It says, how many odd 2-digit positive integers greater than 20 are there? All right, so let's think about the structure. There are 2 digits, so I've got to figure out how many options I have for each digit. It has to be greater than 20, which means this has to be 2, 3, etc., all the way up to 9. That's a total of 8 different numbers. My second part says that it has to be odd. That deals with the last digit. It would be a 1, 3, 5, 7, or 9 to end up as an odd number. So those are 5 possibilities there. So this gives me a total of 40 odd 2-digit numbers greater than 20. All right, the next section is our you tries. So I want you to stop the video and go through and do numbers 8, 9, and 10. When you're finished with those, start the video again and we'll talk about factorials and permutations. Okay, so this says how many ways are there to write a 3-digit even number greater than 500 using those specific digits. So I need 3 digits. It has to be greater than 500, which means this first digit can only be a 5, 6, or 7, so I have 3 options. It has to be even, so to make it even, my last option would have to be 0, 2, 4, 6, or 8. But if I'm looking, I'm only allowed to use these, so it would be 2, 4, or 6. So again, I only have 3 options. The middle one can be any of those digits, so we have 1, 2, 3, 4, 5, 6 total possibilities here. When we multiply that together, we find out that there would be 54 of those numbers. I think that problem got separated and should have been in the last section, but that's okay. Moving on to talk about factorials. Products like 5, 4, 3, 2, 1, when you just multiply all the numbers going down, happens a lot in probability. And so we use a special notation that looks like this. And we read this n factorial. We do not read that n exclamation point. So for a natural number n, the factorial is defined to be that number times the one below it times the one below that, etc., all the way down to 1. 0 factorial would be defined to be 1. So let's investigate this a little bit. So if I have to go figure out 3 factorial, I'm going to do 3 times 2 times 1. Multiplying that out, I find out that 3 factorial is 6. Okay, stop the video and go do 8 factorial on your own as a try me. All right, so 3 says 7 factorial over 6 factorial. So let's think about what's happening here. I have 7 times 6 times 5 times 4 times 3 times 2 times 1 over 6 factorial, which would be 6 times 5 times 4 times 3 times 2 times 1. Since everything's multiplication, I can cancel. So those all cancel, and my answer would just be 7. I want you to do the same thing with 8 factorial over 5 factorial. Expand it, write it out, cancel what you can, and multiply what's left. I'm going to do the next one, the 101 factorial, because sometimes you can take a bit of a shortcut, and that may actually help you with number 4 if you'd like to. 101 factorial would be 101 times 100 times 99, etc., all the way down. Well, that's just 99 factorial. So if I divide that by 99 factorial, this part of the equation is going to cancel. So I'm left with 101 times 100, so I get 10,100. Now let's look at the next one. 9 factorial would be 9 times 8 times 7 times, I'm going to stop right there and do 6 factorial because I see the 6 factorial in the bottom. And then I have 3 factorial, so I'm just going to do 3 times 2 times 1. Okay, so for here, I can cancel those. And so now what I'm left with is 9 times 8 times 7 over 3 times 2 times 1. I can still do a little more canceling to make my life a little bit easier. 3 goes into 9 3 times. I can look at the 2. 2 goes into 8 4 times. And if I just multiply by 1, it doesn't do anything. So on the top, I now have 3 times 4 times 12, or times 7, which is 12 times 7, or 84. 84 divided by 1 would just be 84. So let's look at these last two, because they look very similar. The first one says 5 minus 2 factorial. The second one says 5 factorial minus 2 factorial. So the question becomes, can we distribute that factorial? So let's figure that out. This becomes, do your parentheses first, so this would be 3 factorial, which is 3 times 2 times 1, which is 6. This one becomes 5 factorial, so 5 times 4 times 3 times 2 times 1, minus 2 factorial, which would be 2 times 1. 5 factorial would be 120. 2 factorial is 2, so I get 118. What this tells me is that factorials cannot distribute. Stop the video and make sure that you've done numbers 2 and 4 on your own. Your teacher will expect those done in class. Okay, so the calculator can be used to calculate these factorials because they do get big pretty quickly. So to do this, we would type in the number, and then this is giving you the instructions for using your calculator to make it give you your factorial. So if I wanted to calculate 8 factorial, what I would do is pull up my calculator. I would type in 8, and then I'm going to go into my menu. Factorials are used in probability, and there's my factorial. And if you notice, it puts the little factorial symbol afterwards. So now all I have to do is hit enter, and I see that 8 factorial is 40,320. So this is just going to be 40,320, which hopefully is what you found up above. Okay, so let's talk about probability in general. Basic probability you've studied before. The probability for an impossible event is 0. If it's certain to occur, it's 1. Anything between that is going to be between 0 and 1. Experimental probability, which is also called empirical probability, is just the number of times that an event occurs out of the number of trials that you have. So for example, you observe, let's look at number 2. I'm going to have you come back and do number 1 on your own. A softball player got a hit in 20 of her last 50 at-bats. So the probability that she gets a hit is going to be 20 out of 50, or 2 out of 5. And then the probability that she doesn't get a hit would be the other ones. If 20 times she got a hit, then that means 50 minus 20, or 30 out of 50, she did not get a hit. So that would have a probability of 3 out of 5.